Okay, thank you. So, hello everyone. Thank you for coming, for being here today. Today we have the honor to have Professor Abbas Firoozabadi, who is a professor at the Chemical and Biomolecular Engineering Department of Rice University, and has a large experience in teaching graduate level courses on equilibrium and irreversible thermodynamics. Also, Professor Abbas has a well-established research consortium at the Reservoir Engineering Research Institute in Palo Alto, California. And I think we are going to love his presentation. 2 weeks ago, we had the pleasure to have Rogério Esposito, who several times cited Firoozabadi's work. So thank you, Abbas, for being here today, for having the time to be here with us. It's such a pleasure to have you here, such an honor. Please, the floor is yours. Also, I might say before the presentation starts that Professor Firoozabadi wants vivid interaction with the students, so we are all very welcome to ask him questions during the presentation. Okay, thank you, Abbas. Sorry for interrupting you.
Thank you, Luis. It's a pleasure to share some thoughts on some of the problems that I've been working on in the last 5 years. These are basically the problem in the last 5 years. But as I will mention in the next slide, a lot of the roots of these problems comes from some of the people I have worked with, in the last 10, 15 years. Today I want, again, maybe I should repeat that I have been to your beautiful campus twice. I have stayed there and taught 2 intensive courses when Petrobras had a master's degree program there, and I enjoyed basically being in your campus. It's a pleasure to be back now, this mode, and maybe sometime in the future to visit again in person. So what I want to share with, let's go, I think I will, in the third slide maybe, is there the basic idea. First of all, these are some of the people who have contributed in the last 5 years what we are doing, but some of them also from earlier periods. And the colleagues I have, some of them are PhD students and some of them are postdocs or visitors. Here, for example, and with very different background. Here, Alana actually is the first one. I had a PhD student at Yale, Alana Riodios, and she's now working at ExxonMobil. She did a lot of basic work, and usually when we work with graduate students and postdoc, this is a two-way street. We teach them, but also we learn them. And to me, even when I teach to classroom, from the homeworks of the graduate student, I learn a lot. So this is fun all the time. So again, just to mention of the background a little bit, not all of them. Here, for example, Armando has a PhD in physics. And 2 years ago, he's from Mexico. He wanted to come to the US to do 1 year of research. And he came here and did some advanced molecular simulations that I will share with you. He has a PhD in physics, very different background. And that's make us think and learn from each other. Here, I have a postdoc here. Chanahao Wu is working with me now, and I think he has moved to Rice work with me there. He's working on molecular simulation related to solids and elastic material. Guangzhou Zhao did some work on hydrates, and he has a PhD from Columbia University in geology and geophysics. And the rest of the colleagues in that category, they're from very different places that I will mention their name again when we get to their work. This is basically the main message of my talk, that times are changing. Even when I teach, I think I have to adjust frequently now. Very basic topics. It varies with course to course, but sometimes even when you do molecular simulations, you have to change the emphasis basically. That some areas, even the changes are much more, information and technology is seeing a lot of changes. I think the conditions, which sometimes are challenging, has created the opportunities. And a lot of it actually relates to material science and engineering of new molecules for chemical engineering or chemistry purposes. And I will go through the examples as we make my presentation. 5 years ago, I would have given a very completely different talk or different emphasis. So basically the objective or one of the objectives of my work now is basically engineer new molecules that can be synthesized and could be efficient to change the properties of bulk phase or surface. And mostly related to, nearly all of them, related to energy production, but also environment. Environment is a major issue. And one thing I've been surprised that some of the concepts from thermodynamics, more than anything else actually from what I have been able to use to increase computational speed in molecular simulation is related to concept of stability. The more and more basically I see that these concepts are very, very useful. We have to understand them deeply then. And also what I'm seeing now, some of the issues we have is really what is the surface energy of the solids and fluids. This is the area of very little work, solid work in the literature. So I will just mention, because that's what I'm working on now, but I just mention in passing. Basically, the main issue, one of the issues we have, the climate change. There are all kinds of evidence that in the past 400,000 years, there have been basically 4 periods of global warming. Somehow, these periods associated with the period that has been increased in CO2 concentration in the atmosphere. So here you see from 200 to about 300. The cycles we see, and somehow also methane concentration has been high, but here more CO2. So we see in the past, basically, except in recent past, concentration has been limited to 300 ppm. Now, if you see in this slide, in the recently, there is basically an increase, monotonic increase, basically. So to me, this has all kinds of consequences. Again, this area is very broad, but we could see it, we measure it basically, and we see the link with the past. So somehow we should try to not to dump material CO2 to the atmosphere. It has nothing to do with the pollution, basically. So that's, in hydrocarbon production, fossil fuels, what we produce, basically we put CO2. So somehow we have to worry about burning. And then the issue comes that all this CO2, we should see how we can separate them, either not to produce, which maybe there is not a lot of choice short term, or with CO2 we produce, how we can use it so it is not dumped to the atmosphere or released to the atmosphere. And these are, basically, these are not difficult actually to measure it, concentration of CO2. And what has been done in the past is that you go to Antarctica, take sample of the ice from the subsurface, and then you measure the concentration of CO2 in the ice, and then you try to calculate CO2 in the atmosphere. And actually, I have a book which, and part of my teaching in thermodynamics is actually past climate changes, how we can predict concentration of CO2, how we can predict the temperature. So those comes all from irreversible thermodynamics. And this is, a consequence, one consequence that clear consequence is, with a couple of degrees of warming, we do get, the ice or snow melts. And that's, and there are a lot of other things too. So anyway, one objective should be that we should produce hydrocarbon resources efficiently, but also somehow to use CO2 as much as we can, so the concentration does not go up and lowers down. Now this is basically what I wanted to mention about the introduction. The other thing is that it seems there are a lot of new things that we have to learn, and some of them comes from accident too. This process we discovered very simply just from accident. Basically in enhanced oil recovery, One objective is to reduce the interfacial tension. In order to reduce the interfacial tension, we need the concentration of the surfactants in that the interface to increase from Gibbs adsorption equation. But the issue is that it requires a high amount, even to when you go to the interface. So this is basically, if you are injecting water and we wanted to improve the recovery in conventional process, which is widely studied, the whole idea is to decrease the interfacial tension of between water and oil by, say, 3 orders of magnitude. If you wanted to do that, we have to increase the concentration in the bulk to, say, 10,000 ppm, which is equivalent to 1%. That's a lot of material, basically. It's not cheap, and maybe there's no need to use that much material. So another alternative is that actually don't go by decreasing interfacial tension by 3 orders of magnitude. Here, what the process, and again, is a typo, IOR, not IRO, 100 ppm, only 100 ppm. See, 100 times less than the conventional surfactant. Here, these molecules, these functional molecules, what they do, they can increase the elasticity of the interface. If you increase the elasticity of the interface, that means when the oil goes to small pores, it will not break, basically. And we have just published, the key paper was in 2016, which was on a different basis, but we just have published 2 papers this year. We show how. What you do, basically, you try to decrease the phase angle, which is the measure of interface elasticity, is related to elastic storage or storage of modulus of the interface, which is description of the elastic character of the interface, and also change the viscous modulus, which is viscous character of the interface. You decrease the second one, and the combination provides something called phase angle. You may or may not be familiar with. It's a measure of interface elasticity. All of these we have also for the bulk phase, but I'm basically looking at the interface. A phase angle, if it's 90, basically means that the interface is not elastic at all. It's viscous. Low phase angle, elastic. The interface is basically elastic, fully elastic. It's 0 degrees, and then you can stretch it basically. As soon as you provide a stress, then it will stretch. So that's really the new concept that we are trying to explore further. What we wanted to see, what is the effect of oil-water interfacial elasticity by addition of functional molecule? And the whole objective is that we wanted to use a very low concentration. And CMC generally could be 20, 30 ppm, and you may go somewhat above it. But it is related to CMC and also what happens to the interface. And if you can decrease 2 orders of magnitude, and also all the molecules we work with, we want it to be environmentally friendly, then there is a major chance. Now, there are a lot of aspects that we have to be careful here, because 100 ppm is not much, very little basically. But we are showing you the results, what you do get if we have such a molecule that is can be functional. In general, is that if we have oil and water, sometimes they mix. The way they mix is that we form water in oil emulsion. You can take an oil sample in your lab, let it sit down for 1 year, and then you don't see any water separated. But if you put this oil in a centrifuge, you see some oil at the bottom. Now, this is very common in different parts of the world, and including Brazil, that when you produce the oil has some water in it. So they add demulsifier. And this demulsifier, basically 100 ppm, they are effective, and then they basically separate water from the oil. This is high salinity, what I put here. HS means high salinity water, seawater type or reservoir water. Now, we were actually doing some experiment for just a different purpose, but we noticed that this molecule, when we add it to injected water, we get 20% increase in oil recovery, which we're very surprised. And then we have explored how to investigate it more. You see here, there is a phase angle that I was talking about. I mix and put the oil and water in contact with each other. And then if I look at the case that I'm not adding any functional molecule, this is the interfacial elasticity phase angle. You see, this is about 50, and this is the non-monotonic behavior it has. Now, if you add 100 ppm of the functional molecule, this is what I do. I get a significant increase in elasticity of the interface. And this is salt concentration. I'm using different salt concentration. We go up to, say, 30%. And this is different, basically, type of salts. Salts affect, but the whole thing is that there is a trend with the salt, but the major effect is from very high interface phase angle. I get it to low values. And we wanted to see what is the consequences. I'm working with 3 different oils, basically, and a few different oils. I'm showing that 2 examples here. This is a case that I'm using that oil. First, I use seawater. This is what I get the recovery. Then I use seawater. I dilute it with a DI water. And then the salt content is much less, say, 0.1%. This is the recovery I do get. And this area of low salinity water injection is an area we see maybe about 50 to 100 papers a year. Now, we were surprised that when we take the seawater here, which is the black line, if we add 100 ppm of the chemical, you see I get this improved recovery. So there is not a lot, but it still is more than low salinity water, which, as I mentioned, we see about 50 papers a year, maybe more on the subject. So we have done it with 2 different, very different rocks, and we get similar results. So the interfacial elasticity, which has been the fluid is even more important, but we are finding on other areas of focus in the literature, which is they are looking at wettability and they are looking at IFT itself. So this is what we see with now this is different oil actually. And when put the oil in equilibrium with brine, the water in equilibrium with brine. If we do it without equilibration, without water, equilibration with the rock, and this is basically the phase angle. When I do it equilibrate with the rock, I do get some effect of some dissolution of component from the rock to the water. This is the basically effect is non-monotonic. So one thing quickly we see that actually, even without the dysfunctional molecule that we have added, the literature which talks about low salinity water, the thinking is that the lower the salinity, the better it is, or it's more effective it is. We see that that's not true. So there is an optimum salt concentration for the phase angle, and I'm thinking I'm relating this to the oil recovery. And I think for all the cases we have looked at it, this is the strongest parameter that has been neglected. And this is the recovery now for a different type of oil, that if you do it with seawater, this is seawater. If we add with so this is seawater, and see high saline seawater. Let's not to worry about this part. I don't want to, to confuse too much. So let's not to worry about here. Then if I use it, the low salinity, this part, I get good recovery. If I now do it with the high salinity, with the more seawater salinity, I get similar results. And actually, these are in agreement with what I do get, more or less, from here too. So this means that elasticity is a key thing to look at, and now it's we have opportunity to find out molecules that they can change the interface elasticity significantly. And that will be the best molecule if you can find those molecules. For us, this is just by accident, one type of molecule, and is effective, but there may be more effective molecules. And so that's it. Now let's go a little bit to understand the process. And here what we have done, we have designed a setup, visual setup. We put here water and we put oil on top of it. But since we wanted to take camera, we have simple techniques. We are going to dilute the oil. Therefore, the problem is changing, but maybe the mechanism will not change a lot. The numbers will be different. So I'm going to see what is the effect. Now you see that here, if I look at the interface, when I add the 100 ppm molecule, you see that very quickly, what I see that I'm going to get, basically, these are times, basically, right away, after half an hour and an hour. You see that at the interface, when I put the molecule, I'm going to get a lot of structure at the interface. So what this molecule that changes, and that's what interfacial elasticity is related to a structure of the interface, not the bulk phase. On the other hand, when I add this molecule, we make this structure here. When I initially, without adding it, is similar to this. But when I add the molecule to the bulk phase, basically, this is what I do get. So this molecule does two things. One, it eliminates structures, these type of structures in the bulk, but creates interface elasticity, interface structure, and that's what it does the work. In some oils, I don't get actually this structure. Still, it forms this structure. So this basically elasticity is related to the structure of the interface. So this is my concluding remark. A new process for IR based on interface elasticity. Extra low concentration functional molecules may be more efficient than the conventional processes. The whole concept is based on molecular structure at the interface rather than in the bulk. I think in our case, basically, we were lucky. We were doing experiment in the lab, we see this is happening, and then look at it. A lot of time, this is what happens. You have to do the work, basically, and something may come. Sometimes may be lucky, sometimes may not be. So that's the couple of main conclusions. I'm going to go to another topic, which is related to some changes we have to do in the bulk. This relates to CO2, which has many different applications used. There are three applications that, two of applications I will emphasize, but also viscosification is important, or even sequestration, putting CO2 under the ground in aquifers. We have a number of papers on the topic. If some of you are interested, may look at it, but the key papers are in preparation state from our work. Now, just to give you an idea on some of the good things we see from CO2. This is the only pilot project in the world that CO2 is used for fracking the rock. And here, CO2 fracking is very different than water fracking. So somehow surface energy gets involved that we are trying to understand, maybe others too. But also when you crack a rock, you wanted to put in it some sand grains. They are called propanes. If you have water, the viscosity is high, they can carry this sand and grains. But if you have CO2, the viscosity is low. So it settles basically quickly. So you need to viscosify CO2 for these particular applications. So in this project, what they have had few wells, and then when did hydraulic fracturing, basically there is not much benefit. You create the fractures, but there's not benefit because water goes and blocks small pores. But if you do CO2, this is not the case, and you get a lot of benefit. The only problem here is that the molecule which I've used, I talked about, is extremely expensive and is not also environmentally friendly. So we have to, in this purpose, we have to synthesize new molecules. So a couple of years ago, I became interested. So first thing was that to go to look at the literature, and then I will share with you. But the statement of problem is given here. As I have stated here, generally carbon dioxide has gas-like viscosity and liquid-like density in the subsurface. A higher viscosity basically helps enormously with efficient displacement. In Brazil, in subsalt, what you do, you have a lot of CO2. You actually don't dump it in the atmosphere. Credit should be given to Petrobras and Brazilian government. They inject it in the formation, but just to increase the sweep efficiency, they combine it with water. Is called the process called VAG. That helps basically. But if you can increase the viscosity of CO2, the process may be more efficient. But now it's very costly. The three application for CO2 viscosification. One is fracking. The other one is for improved recovery, which can make it much more efficient if we can viscosify CO2. And the third one is sequestration, that we can put large amount of CO2 in the aquifers, deep aquifers, but all of three of them, we need viscosification to make the process more efficient. This is actually the work we did with Rogerio that visited you 2 weeks ago. This is a paper, SPJ paper in 2013, that we have simulated the type of work we did with Petrobras. And this is CO2 and this is oil. CO2 in Brazilian conditions is heavier than the oil. So goes basin is heavier. This is what we do, get oil here. And now if I can viscosify 10 times, this is what is happening. So it basically is piston-like displacement, which basically is much more efficient than this process. So this is one objective. Now, in the case of injection in the hydrocarbon formation, if you inject water, this is what you are going to get. If you inject CO2, you get this because of early breakthrough and inefficiency of sweep. If you do it VAG, which is what Petrobras does, this is you get improved. But if you can viscosify CO2 10 times, this is what we do. So that's what we are after. Now, just to give you another example is that if you have a piece of rock, you wanted to break it, what you do, you can make a hole in it, increase the viscosity of the fluid, or by mechanical means, you can change the stress. And when you increase a lot of pressure, that means you're changing the stress. If you use water, this is going to be the pressure at which the rock breaks. If you use supercritical CO2, this is going to be the pressure at the rock increase. So all the experiment in the lab indicates that, at least in the case of shale, the fracking pressure, the breakdown pressure, or the stability of the surface very quickly affects the surface will quickly affect the stability of the rock. And this example is for the liquid CO2. This is for a supercritical CO2. This is for liquid CO2, and this is water. And there are many examples in the literature. We can see.
I have one question. What's indicating the pressure? The pressure is that the pressure that the surface resists, or the pressure you provoke using the fluids?
Basically, what we do, make a hole. Just to go a little bit detail, we make a hole and pump a fluid in the hole. The function of the fluid is that when you increase more, the pressure goes up, but it changes the stress. When you go to the rock, basically, there's a stress and a strain. So the fluid creates the stress. I can do it in vacuum. Actually, I can increase the stress in vacuum by exerting force. So the function of fluid is to increase the stress. But somehow, and that's the part which is unknown. But somehow, although both of them create a stress, the stress which is created by the fluid or by CO2 in this case, the effect is different than the one by water, and is different than the one by vacuum. By vacuum, although they have not done it, if I had just done the stress or applying the pressure to give that stress, is even higher than this. So there is one part of it which is a stress, which is people. The reason is that actually this difference people are relating to even viscosity, because they think if a crack is created, the fluid moves faster, but that's apparently not the case. So again, somehow is related to surface tension. Sorry, the surface energy. There is one theory in the literature that says if we take a rock and put it under tension, you do work basically. If you put too much tension, it's going to break. But the work you do on the rock is going to be stored as potential energy in the rock, potential energy for the molecule, increasing it. And when it breaks, all this potential energy helps to create the surface and the surface energy. So there is a theory in the literature which 110 years ago was introduced. And we are actually trying to, this is just stated, the genius make this a statement, and it comes from a different background. We are trying now to calculate the surface energy and to explore it. But again, two effects. One is with a fluid, you change the stress. When you change the stress, there is a limiting stress that the rock will break, basically. And these are all like nucleation in fluids. The other one that we are trying to understand from the view of the surface energy, because surface energy also plays a role here. And we are just trying to understand. I don't know if this was the answer to your question. Is it clear?
Is it? Thank a lot.
Could you repeat?
It is. Thank you a lot. I understood.
Okay, very good. Thank you. Okay, now let's look at the type of molecules which has been looked at for increasing the viscosity of CO2. In other words, what we are interested in, you have CO2 at certain condition of pressure and temperature, the viscosity is very low, say 0.1 centipose, even less. You wanted to increase the viscosity of CO2 by 1 order of magnitude. And there are ways to do that if you also dissolve some molecules in it that can dissolve. In the bulk term, you can do it, but we don't want to have a lot. We wanted, 1 or 2%. And one problem with most of the molecules in the literature, you need the 3-4%, basically, one group of molecules, but we wanted actually less than that. So we wanted to engineer the molecule. But there are basically two types of molecules which has been reported extensively in the literature. One of them is polymers which are fluorinated. Fluorine helps for the dissolution of polymers CO2. Polymers in CO2, they dissolve very little. Even when you go to heavy hydrocarbons, not like alkanes, if you have a 30 carbon alkane, solubility is less than 0.1%. So the polymers don't dissolve in CO2 unless you get functionality that changes, and this functionality in the first group is by fluorine, which is expensive, basically. And then maybe the fluorine, the polymers, they have alkane tails. P1D is one example, which is poly-1-decene, and PVEE is another example. But these two molecules, they increase it 2 or 3 times at higher concentration. The only one which increased a lot is fluorinated polymers, which are extremely expensive. And let's see what these molecules do and what is the results. Here, there is, this paper, although is from 2000, but there is, many papers in the literature and that they have this type of molecules have used with different functionality. And this is the concentration in CO2. This is the viscosity increase with respect to CO2. You see that here, if I add 1%, this molecule, the increase in viscosity is, say, 3, 4 times, 5 times. If I add, but this is exponential. If I add 4%, the increased viscosity 200 times. Very appreciable. But the problem is that I need 3 or 4%. This molecule, you see that the cost is 200,000 per kilograms. Is out of sight, especially with today's oil prices. So we have to engineer molecules that are effective, that are also inexpensive. This is a different type of molecule, which is poly-1-decene. This is with 6 monomers. And this molecule dissolves, these chains helps, brushes, help with the solubility and then viscosity. And we do get, you see that this with 4%, you get about 3 times. For 5%, you get about 3 times. So this means basically this molecule, although is desirable, but this particular molecule you need large concentration. It's cheap, but it's not that cheap that you can use it a lot. And it's not serving the purpose. We need, for common applications that we need increase of, say, 10 times. This is a different type of molecule, which is even less effective than P1D. This is more costly, and this is relative viscosity. So for me, actually, for us, in order to see why these molecules increase viscosity of CO2, what I did when Armando came to work with 1 year, I asked him to basically, write communication, because of the computational speed and the polymers, they are, big molecules, so we cannot use simple molecular dynamic simulation. We have to use dissipative particle dynamic simulation, which is basically mesoscopic simulation. It somehow has the accuracy here, and there is an increase in computational speed by a factor of 3 orders of magnitude if you use DPD for this type of calculations. And first, we wanted to see molecular structure in CO2, then see how the viscosity does. So again, if you use DPD, you have to put group molecule atoms together, and this is the representation of the molecules that you have used by DPD. So, and then it's completely different basis than molecular simulations, and one can go through it. And this is the representation for DPD, which is mesoscopic simulation. Now, this is for P1D, and this is what we see that basically the molecules. There is no aggregation, but there's no association, basically. And for different concentrations, we have used. And this is what we do get, basically. So there's no association. So it seems that somehow this branching helps. And now actually we have taken this idea further, and we are patenting a new molecule that seems much more effective. This is again the same type of molecule, but what we call it PVEE, and it associates, basically. It becomes bigger molecule, and that's basically what it does. So it basically associates, become a bigger molecule, and that's to its functionality. And this is now, water has a big effect. Small amount of water has a big effect because water promotes further aggregation. So this is like a water in oil in water emulsion, actually. In my cells, actually, we need a small amount of water to get this to the core, the molecule together. So water helps 20-30%, and it does aggregation. So because the experimental data was there, we wanted to test our model. And then this is the molecule which is effective. This molecule has aromatic rings, so there is pi-pi stacking, and basically there is association, and so the stacking is important, and that's really contribute, and that's the molecule is big. It associates also, so that's what is effective and increases the viscosity significantly. So, and then, there's all kinds of experimental work showing that with this molecule, if you increase the aromatic rings, the effectiveness increases to a point that there is going to be interfolding, which does not. And then we basically compared the simulation results with molecular simulations, and we saw the result. These are experimental work, and these are comparison with the molecular simulation. We can simulate it with molecular simulation, understand it. And then now the problem, when I was reading some of these papers in the literature, I was a little bit concerned that it's true that you can viscosify even and this molecule with fluorination, you can increase the viscosity. The problem is that in the rock, it will not work. And in the paper we wrote, actually, there was no report of that. We just had a word of caution that this molecule may be absorbed. So when you put in rock, will not be there to viscosify CO2. So just recently, a group has been working on fluorinated molecule for a long time, for some 20 years. They did some testing in the core rock, and they found out that this molecule, with the pressure drop is very low if with the CO2, if they put polymer in it, which viscosifies CO2, absorb to the rock enormously. So they basically plug the rock, and that's very detailed discussion in this paper that even these molecules, which are very effective, will not work in the rock. So at the same time, we have to worry about the absorption. We don't want to have absorption, basically, to the rock. So way forward, this is what I have here, is basically we have analyzed whatever was in the literature we could find out, and then that helped us to engineer a new molecule, which we think we have now two molecules, much more effective, but the area is wide open. And we also require, whatever we do, initially we are looking at absorption. And we are using molecular simulation basically to figure out the absorption. And we are using a steered molecular dynamics simulation to look at the absorption. We'll hopefully have a paper in a few months on the subject. So this is the, I have two other items, but this is the another major talk. And another part of my talk related to structures in hydrate systems. This is actually a picture in the literature, which apparently is from Petrobras. I could not find the source of citation, but from friend, I have learned that this came from offshore Brazil, that they have hydrates. You see, and you have something like this, you're plugging the pipe. So we wanted to add some molecules to prevent hydrate formation. Petrobras has been working on the subject for a long time. I'm sure some of you in Brazil have been engaged in research on the topic. Basically, hydrates means that if you have methane and water together, they form such a structure, which this is methane, and the rest of them, water surrounding methane, forming these cages, and there are all kinds of molecules structure. So from molecular simulations, maybe 10 years ago, 12 years ago, a PhD student at Colorado School of Mines reported success with using molecular simulations to basically predict the molecular structure of hydrates in these cages. And this is for methane hydrate, with this system is simpler, maybe something like about 50 molecules form certain structure. But if you go a different class of hydrate, which is called S2, then maybe 150 molecules of certain structure. The second one has not been done, and that's what we did when we were looking at the molecular simulation for both. And also the main objective was examining different types of molecules that they are effective at low concentration to prevent or mitigate hydrate formation. Just to show you a little bit what is done, this is a cell that we have. You introduce methane and water, put the condition of hydrates, and then try to see when you get hydrate. If you do it, basically, when you get hydrate, it's going to be crystals, basically here. What these molecules do, maybe you can have it in terms of a solid like this. You could have it hydrate. This is a slurry, water and hydrate together. And this is the condition, but it doesn't, the molecules don't aggregate. So what we wanted to do, understand, we had one molecule that was very effective, better than what we can find in the literature, but we wanted to understand the process. So this is a hydrate plugging. This is a slurry which we wanted to have. So this is basically the process. You see, this is very effective. But even when you form hydrate, if you have these molecules, it will be powders. We were very surprised, actually, that this molecule is so effective over the whole range works. And in this case, as I mentioned, even if you form hydrate, is not a crystal, one piece of crystal. So that's what, then we wanted to understand it. And again, this is the work we tried to repeat first, the work in literature on methane hydrate structure. And the work which was done before, it took microsecond computations. We incorporated very simple concept, and there was a speed up, 3 orders of magnitude that I will share with you what we did. So this is basically the molecules. You put the methane and water and maybe salt too. And this is the molecular simulation, get the structure. But what we did, basically, we included one concept from thermodynamics, and there was 3 orders of magnitude increase in a speed. And even with the case of propane, if you don't apply the technique that I will talk about, it will take a long, long time to get the structure. But with this incorporating thermodynamic stability, actually, you can increase 3 orders of magnitude the computational speed. The way people do the work is that they put methane here in contact with water and the conditions that there is hydrate. In this case, actually, they have to have a low temperature, lower than what it is, say less than 250, to get the hydrate nucleate and to get this structure. This is our approach is that what we take water and we calculate the limit of stability of CO2 in water. Water can dissolve CO2 0.15%. But at the limit of stability, you can put up to 10%. So what we do initially, we put 10% CO2 in water. Now, and then actually we don't have to go 250. We can go a temperature very close to measurements, 285, which is closer to measurements. And then we could see hydrate formation because we have the C1 molecules already in water. In this case, what we notice is that if we put methane more than limit of stability, suppose the limit of stability is 10% C1 in water. If we did 10.5%, within 2 femtoseconds, methane separates from water. But if we go below limit of stability, we see that during whole simulation, water will not pop up. So that's really what we have done. This is comparison, what we have done. This is literature, time it took to do this. This is going to be microsecond 1.2. In our case, basically, at different temperatures, we can do it. First is 250, we can do it 285, which is closer, basically. And you see basically the speed 3 orders of magnitude here. I don't have the numbers here. So basically, very simple concept from stability on terminal. And this we see in a lot of other areas that when we implement some of the basic concept from thermodynamics, somehow we can do things much more efficiently and more accurate. Now, it came here that we wanted to see the structure of different hydrocarbons and different polymers in water, and also how they absorb on the surface here, on the surface of hydrate. This is the hydrate, which is basically is constructed and put in. And here we wanted to see also the effect of the salt. So these are 3 molecules. This is the NC10. We just wanted to see what happened to NC10 because hydrocarbon affect the hydrate process, formation process, and even mitigation. This is a molecule that we have, we work together with Lubrizol, and this is the molecule which is Shell. This is Shell's molecule. And we wanted to see this molecule, our molecule is much more efficient than here, especially it works all the ranges of what we call water cut and also salt concentration. So basically, this is now when we have hydrocarbons in water, this is the structure actually. Even in this case, there is going to be structures around the hydrocarbons. And this is salt. I will not go to details of the structure. But this is NC10 is water around it. And this is when you have salt, the salt basically is going to break some of these structures. This is the molecule that we found effective. This is the structure it has. And with the salt, it's become somewhat less effective, but not, it still works. And this is the molecule which is from the Shell, patented by Shell. And this is the structure. As well as to see what is happening, actually, if I put C10, this is water and salt, this is the hydrate, methane hydrate. Let's see what is happening to this molecule. And I have periodic boundary condition. So this is what is happening, you see, towards the end. I just one molecule free, but the molecule, this hydrocarbon, like the surface of hydrate, actually, comes here and it stays there. So it's even hydrocarbon is helping. This is our molecule when you use it. So really lays on the surface. And this is the molecule, which is, which was thought to be somewhat effective in some conditions. I'm putting it in the system. For this range of water conditions, is not effective. You see that it really doesn't like the surface. It goes close to it, but doesn't get absorbed. And this is, based on some ideas we had initially. Actually, this is the way the hydrate, this molecule we have, both the head and the tail somehow get on surface. This is actually before we do molecular simulation. We had some ideas, and molecular simulation reinforced it. So this is what this, and this is the last item I want to talk to see how much time do I have so I can wrap it up.
You have plenty of time. You can go on. No.
Right. Basically, now we are somehow interested having confinement, and confinement is a solid. And then we wanted to understand the flow process and adsorption. And there are all kinds of issues actually when you go to the solids. And then deformation, which is much less work and a different track. So that's what I'm actually trying to do. Try to understand the stability of rocks and to see how to account for them. A lot of people who are doing this problem, they come from the fluid side. So they try to extend what we know about the fluid to solid. Maybe we cannot do it. In solid, one difference with the fluid is that in fluid we have pressure, which is a scalar, and you have volume also. In solid, we have a stress and a strain, and both of them are tensors. So there's a big difference between them, and we have to actually account for them properly. And I see issues there. So hopefully, as work progresses, we publish others too. One area which is important in the world is shale formations. Shale formations where there is a lot of natural gas and light oils. Shale is very different than other types of rock. First, there is the organic part in the rock. This is just like asphalting, a bigger molecule, and has become basically the place where most of the fluids are. And this is the inorganic part, the other types of rock we do have. And usually here, the pores are small, and this is where it is when it's the fluid reside. So we wanted to understand fluid behavior here. This is the molecule which most of the time, or most cases, comprises the organic part. It's called kerogen. And this is the molecule which is actually, I found this from dust in the outer space. There is some kerogen molecule, similar to asphaltene molecule, but it's much bigger. And the other difference is that unlike asphaltene molecules, kerogen molecules not soluble. They are not soluble in aromatics. The basic measurements is difficult to make in shear rock, and even sometimes macroscopic measurements. So we have to go by molecular simulations actually to understand a lot of things. Molecular simulation is becoming just going to the lab and doing experiment. As I mentioned here, I've been doing it recently, but it seems molecular simulation of enormous value in the understanding and interpretation of lab measurements, or basically actually do molecular simulation first to design the experiment, or even just molecular simulation may provide the answer. So one part of it is related to adsorption. And these are what we can do. We can look at this type of structure, this part of the structure that I have here. Now, actually, what we do here is that from individual molecules, these molecules, we put together, and through annealing process, we construct the porous medium. So we start from molecule putting together and making the solid. Because these molecules also are flexible, they're not crystals. So we should allow them, even when we bring fluid in contact with them, we cannot assume that these molecules are rigid. So just like polymer, they are flexible. And here we have done all the steps, and we are seeing how is adsorption or total uptake, what goes inside the porous media, all of it in a shear rock. And we see that CO2 has the highest adsorption. So that's good. So maybe also CO2 we can inject in some of these shear formation for different purposes. One of them actually we can store it is adsorption is more than other hydrocarbons. But it's not only adsorption, there's other complexities actually that it also dissolves in the rock itself, and we can predict that. Not here, but we have a material that will come to the literature showing that how to account for it. So here basically you see that CO2 has higher adsorption, and then to every molecule adsorption is less. Now, also one thing is that because this is not rigid, it swells, expands basically. If you bring it in contact with CO2, so it shows that CO2 swells the most. Now here, what I don't have it is these are all gas fluids. If you have it liquid, the swelling is maybe 5 times, 10 times more, especially for heavier hydrocarbon. There is all kinds of also issues in the literature that one has to look at it to see if you can get prediction for molecular simulation. For the liquid is simple laboratory work, but for gases at high pressure is not simple. And to the best of my knowledge, for the case of kerogen has not been done. So this is one aspect. The other aspects relate to even flow in nanopores. There are 2 papers about the same time. One of them is Science, the other one Nature, that shows flow in nanopores are much more than what we predict from Cruson diffusion model. And I think let's stay here with Cruson, because the other ones, if we go to some other macroscopic, the error is larger. But we see that with a Cruson-based model, we get 40 to 120 times more for some of these systems. So the question to me when I read these 2 papers was to find out why we have such a high enhancement flow in nanopores or in simple systems when the diameter is very small. And then we did the molecular simulation work, and that's what this basically very briefly shows, that in the close to the adsorbed layer, the density is much higher, and in the middle is near close to the bulk, and then the velocity is not that different. The adsorbed layer is also moving very fast. So that's what we get from molecular simulation. If we go through details of simulation, so it's really the movement of adsorbed layer which is contributing to enhance flow. And the next item is that these are new items we just published, is related to a test they measure tensile strength. Actually, this type of test is called Brazilian test. So maybe it was done first in Brazil. So you take a piece of rock, and extend it from two sides here. You put certain element, you can extend it. And after some condition, the rock is going to break, basically. And then you can do all kinds of measurement. This is the machine setup that they are using. So the purpose is that to see if you can predict this breaking from molecular simulation for kerogen. So this is basically what you have. This is initially the piece of rock. What you do, you here put it under tension, you stretch it. And the other one under compression. You want to see what is happening to the rock. So it's going to volume is change. You are going to get basically mechanical properties from here that is used for in all practical applications. So here basically we work with a system that others have done, and this is very well type of elite. So basically you have this system, you try to extend it from both sides. And then you are displacing all the atoms in every step, say, or in some steps by 0.5 angstrom. And then this is what you do. This is a corrosion. You see it's extended, this is what is happening. If you do elite, you see it's different, basically. It's just, break. But here is going to be a process because of flexibility of the molecules and the way we have done it. And then you can get stress versus strain for this type of corrosion. This is the paper which I mentioned was published this year. And then you can get actually both compression and extension, which the Young modulus is the same, and this is at different stages. When you go above a certain stress, still I'm to switch if my pointer moves. Okay, yeah. Here, basically, this is the elastic region. This, you get it into plastic region. And here is reversible. If you reverse it, you get back. And these are at different confining pressures. Basically, you put confinement, and then you try to stretch it. And this is basically showing this is the elastic part in both on the compression in compression and strain. The Young modulus is the same. It's reversible, and then you go to this region, which is the plastic part. And this is basically what we have done. This part, you see, you go back, but here, if you go back, you get, because it's a plastic region, both in the case of the extension and compression. One of them is positive, the other one is negative. Now, again, I'm just talking about this slide, and that's what the focus of my work is now, is basically how to get thermodynamic functions related to solids. Some of the work I see in the literature, they neglect this term, the work from compression and tension. But if you include it, you see these are the usual thermodynamic functions, and closed system. So this is the surface energy, basically. But this is this additional part due to a strain and strain that makes things more complicated. So a lot of authors in the literature use this actually for the same problem. This is neglected. Even if I think one paper we published, we neglected this along with the literature, but now we are seeing we have to include that term. Is obvious now why we have to. When you go to fluid, actually, this problem becomes simpler. You see, this is for fluid, dV basically, but here is different. And then we are in the case of the pressure, this basically becomes a scalar. So again, I'm just, this is just a point here without showing any result. What I see that actually when you use molecular simulation, my experience is that we have to combine with classical thermodynamic concepts of fluid and solid. That may help us. Yeah, I think for our application, the area is wide open. And again, hopefully we'll have some graduate students from your school come and help us to move forward. And finally, I wanted to acknowledge the institution that they help us. Petrobras has been supporting for a long time. Through some period, Petrobras was providing funding to Federal University of Rio de Janeiro. So for 2 years, the interaction was for Federal University of Rio de Janeiro and the other companies that they have helped us to work in the area. And thank you for the opportunity. And then I will be happy to learn from your questions and have discussions.
First of all, thank you a lot, Professor Abbas, for this meeting. First of all, if I'm not mistaken, in the start of the speech, you talked about lowering the viscosity of water and oil. Am I correct?
No. There are two things basically. In the first part, I'm talking about lowering the phase angle, which is related to interfacial elasticity. I wanted to change the interfacial elasticity.
You wanted to change the interfacial elasticity for what? Lowering the pressure drop when you're bonding?
No, for the purpose of, that is not for the pressure drop. Basically, you see, this is for the purpose of oil recovery. Suppose you have oil in the formation, you wanted to displace it with water. If displace it with water, you get only 50% of the oil. 50% remains in the rock. Part of this 50% because you have broken down the oil into small pieces. If the oil interface with water is very elastic, the oil will not break down, will deform when you go through a small pores. So I wanted to make the interface between oil and water elastic. Just if you have a running nose. You see, you have a running nose, you see that when the fluid wanted to basically leave, it's going to stretch. If we didn't have high elasticity, it would break basically. So the elasticity is different than interfacial tension. So in the first part, I wanted to increase elasticity of the interface. It has nothing to do with the viscosity. If I increase elasticity of the interface, I have higher oil recovery. And the surfactant injection for IFT works a very different process. But you need a large amount. So here, the chance is that, what we have found in one case is that we have 100 ppm, we may increase the oil recovery. And that's through interfacial elasticity. I wanted higher interfacial elasticity means lower phase angle. Phase angle, which is a measure of viscous and elastic modular. So that's the first part. In the case of CO2, what I want to have, I wanted to increase the viscosity of CO2. If I increase the viscosity of CO2, I will have a good sweep of the displacement of oil by CO2. So that is.
So what I want to ask is, first of all, how do they apply this technology in the industry itself? Is it already applied?
Right. So I think the company who has sponsored the work on the interfacial elasticity is actually working on designing a pilot. All you do, you are injecting some seawater. All you do, you add 100 ppm of this molecule to injection water. So that's it's very simple. And because the amount is small, offshore they can do it too. One problem is that in offshore, if the amount is 1%, you need a storage, big storage, you cannot do it. So that's really the application of technology. And then you have to do engine calculation to see how much increased recovery you are going to get with different conditions. So that's really, on the case of CO2, is not only, I brought one example that has been tested in China, but there is, this is a suggestion basically to move in that direction. And also for sequestration, I have one of the companies in Norway, they wanted to go have more efficient CO2 sequestration and wanted to know where the CO2 goes to have better control. So they are very interested in CO2 viscosification. And then there's all kinds of other applications. Even I did not talk about it for the case of CO2 fracking. Also, when you put CO2 in the earth, there is cap rock at the top. If the pressure goes up, it may break. So it's important to know when it will break. So there's all kinds of applications.
Understood. So the part, I could hear the part of the CO2, but my internet failed a little when you were talking about the oil, water and oil part. I'm sorry, could you repeat? I will turn out my sound so I won't fail.
Okay. This is for the case of CO2, basically, is it? CO2 viscosification, is it? Is it CO2 viscosification part?
The CO2 is understood. I couldn't hear the part when you were talking about the application of water and oil.
Water and oil was the first part. Okay.
Yeah.
The CO2 is not water. The CO2 is here. Okay, let me show you. Are you looking at? Okay, this is at the very beginning. Okay.
Yeah.
Is it here?
Yes.
Okay. Basically, first, there is a paper that we have in Langmuir. This paper, that's describe the process somewhat for the but basically what we are doing here is that you see here, in the case of conventional IOR, it's very clear what they do. They add surfactant to reduce interfacial tension, and that in order to, and they needed 3 orders of magnitude decrease. So they need, 5,000 to 10,000 ppm. And also these molecules have issues too. This molecule 5,000, 10,000, if they do it at high temperature or high salt content, they will absorb actually to the rock. So they will not surface. The molecule that we have does not want any other surface except water and oil. It does not like to go to the rock surface. It will not absorb. And this paper is described. So basically, the idea here is to increase the elasticity of the interface and measure the elasticity is phase angle, which is related to G prime and G double prime, which represent elastic and viscous moduli. And then here, basically, this is actually the rest of it that basically this molecule we are using destabilizes emulsion in the bulk. Here you have emulsion in the bulk, water emulsion, water oil emulsion in the oil. If you add this molecule 100 ppm in the oil, basically the water separates. So that's where to use it. When we're doing some experiment along this line and core flooding, we found out that when we add 100 ppm of this molecule to the injection water, we get 20% extra recovery. That we were surprised. And then we continued the work and we found out that basically when we add 100 ppm, we get lower phase angle, much lower phase angle. And it means that lower phase angle means elastic. When the oil goes through the small pores, it deforms, it does not break. And without emulsifier, this is what you look at. And this is with salt concentration. See, this is jump, or this drop is the one which is, if it happens for a specific system, is helpful. And this is what I was showing, that oil recovery with seawater. Oil recovery with low scientific literature. There's all kinds of 2 or 3 reviews actually on the subject, and wrote one of the reviews. And then we add 100 ppm of this molecule, then you see the recovery increases. This is not a lot, but is that the trend? So this means that the interface has become more elastic, so oil, when it goes through small pores, it does not break. And this is, the effect of when you do measurement, it seems that for low salinity or low salt content water, we have to put the rock in equilibrium with the water, injection water, because some of the components from the rock may dissolve in rock dissolve in the water. So we have to use water that has been equilibrium with rock, but it seems that the effect is most when we use DI water, deionized water, because deionized water doesn't have ions from the salt, so it accepts more ions from the rock. For the others, the effect of equilibration is not much. And then this is other experiment. This experiment, we use seawater injection. This is the recovery. If you use DI water, we get even this. If you use, sorry, this is DI. Sorry, this is seawater. This is low salinity water. The green one is low salinity. We are not looking at this part. I did not explain why we did this part. We see that if you use low salinity water, we get high recovery. But if you use seawater or any type of water, inject with 100 chemical, you do get the same as low salinity. In the previous case, low salinity water was not efficient, but in this case, low salinity water is efficient as our chemical. But our chemical, you can add to seawater injections. You don't have to remove the water. Even you can add produced water, which has much higher salinity, and you get similar results. So, but as I mentioned, this molecule, we just got one molecule from accident or from luck, and we get good results. But now it will be good to look at into see if you can other molecules which are likely to increase elasticity of interface more. So is that clear?
Is it? Thank you. I have another question, but that's not so technical. So what's the barriers in your research? What's the difficulty you may face when you're researching a new molecular engineering? What?
No, basically, there's like anything else. Some people from the industry, when you talk about simulating molecules and getting knowledge from molecular simulations, they are hesitant. They think that this is academic exercise. To me, I'm looking at it actually just like going to the lab and doing an experiment. In the lab, when I go, if I'm not careful, I make all kinds of mistakes here too. So to me now, it has become a tool, molecular simulation, that you can do basically through research, in a sense that, replacing experiment, or you understand the experiment, because when we do experiment, always under certain condition. When we change the condition, the experiments, they are not helpful. For the work we are doing on viscosity of CO2, it's very difficult to measure at different conditions viscosification. So if you have a molecular simulation or a tool that you can create and verify what you do, and then you can predict other conditions. So I think we have to convince the industry or the sponsors that molecular simulation is something that is just becoming more and more useful, and that's an area we have gone. The other thing is that in all areas, we always create new molecules. Look at the virus. They are putting things together to have new molecules which are effective. The same thing here. So it's just, you have to do more. You have to create the phase, and so sometimes that's not easy. But, I have, with the companies I've been working, actually, they're surprised, and they want it. Now, for the government funding, if you have molecular simulation, is helping, because they like new things, basically. So I think that, like anything else, we face problem. You have to change some of the concepts people are using. I'm working on another area on asphaltings. We just found out that you have to completely different from, if you wanted to simulate asphalting in flow lines or in the wells, you cannot use what they have been doing. You have to do completely different and much simpler. So there is no doing anything new is difficult. You have to convince the students, others, but the good thing is that convincing a student is very easy. You give good and the response is good. But in
the guys with the money, it's hard. So it's funny because we used to hear here in Brazilian university that's hard to convince, especially the private system, the industry, to finance research because of that idea that it's just an academical thing, it's too risky. So it's funny to hear that's a problem not only in Brazil but here in
all over the world. All over the world, yeah, sure. But I think that's anything new. When you tell people, for example, if I'm interested in bulk properties, I can use 200 molecules. I can get bulk properties because I use periodic boundary conditions. So that system is large. Computation is, not a major. So it's difficult for people to get that idea. So it'd be time.
Thank you, Abbas, and thank you, Marcelo, also for the discussion. I just want to ask anybody if other people have questions. I think that's a good opportunity.
I don't want to monopolize him.
Hello?
Yes. Abbas,
you continue? Yes.
We can hear you. So we are open for questions or comments if anyone wants to ask questions. If you want, you can also ask in Portuguese, and then we can translate to English if it's needed.
Yeah, I think while may others may be thinking in their questions, can I ask a question, Luis and Abbas?
Of course you can, Rodrigo.
Okay, thank you so much for the presentation, Professor Firoozabadi. I would like to stay in the slide that you are transmitting right now and ask if you also changed the ppm in the de-emulsifier to see the influence of the emulsifier concentration in the oil recovery, and also if as we also know, in the oil well during the time, the composition between water, the salty water from the sea, and the content of oil, and also the oil composition changes during the time. Are there any studies to see if the same study that you presented here with the same parameters can be transferred to over time in oil extraction?
Yeah, I think very good question. First, on the change of the constant, we have done it actually. And we have done it from, say, we have used 100 ppm. The limit of solubility is close to 200 ppm. So we had 200 ppm, and it's in one of the two papers that I have listed. There is no difference, basically. So we don't need actually more. The other thing is that a very important part here is that, it seems indication there is no absorption, basically. So there is, in the same paper, actually, we have measured dynamic adsorption. If the molecule was going to adsorb to the rock, this was not effective. The other thing is that, as you have seen here, the answer to your question is somewhat here. You see, this is the effect of the change of the quinate water, seawater, other types of water. There is some change, but it's not pronounced in this case. And we have seen other cases, even the effect is less. So the good thing here is that the effect is not very pronounced. If we change it, in other cases, actually, we have seen nearly flat. Now, the only thing we don't know at all is that because we have done work with 10 different oils, we are seeing that in some cases, the process is effective. In some cases, it's not that effective. And then this depends on some of the molecules in the oil. So what at this stage we are suggesting is that let's do the measurement, basically. And I think what we see that without exception, the phase angle is related to oil recovery. Those of you who have done core flattening or, working with the rock is very difficult. But we see that actually for this test, maybe this value is very low. I think that the recovery is, my perspective that the recovery is going to be high. There is no need even to do core flattening. So it's not that much affected actually by the rock. and also that much affected by the type of water, only affected by the type of oil. And the type of oil, we know that is not really methane content. Ethane content is the type of heavy material, aromatic material in the oil may affect it. But these things we will understand more when we can get something like this from molecular simulation. So we get some insight, but that's going to be a way away.
Thank you very much. I think I might have other questions about other sections of the presentations, but I would like to wait a little bit and see if anyone else want to ask you.
Sure.
So, guys, have any questions?
Can you hear me?
Yes, yes.
Good afternoon, Professor Abbas. Thank you very much for your seminar. I was a bit curious about the pressure cell you showed for hydrate formation, and I would like to ask what kind of information can you get from experiments in the cell? For example, can you use the cell to build equilibrium curves? Do you work mostly with kinetics? Do you look for hydrodynamic aspects?
You are talking about these cells, basically. Am I correct?
Yes.
Right. These cells, basically, the most important element of them is visual observation. So these are, you can go very high pressure. You can see the whole content of the cell. You see here, for example, if we did not see them and we were inferring this from different measurements, it would have been difficult. Actually, we are using this setup now for solubility measurements of the polymers in CO2. And the good thing is that we see directly, basically, what is happening. So the good thing about this cell is visual observation. And then, you can do analysis based on what you see here. This we have connected to a viscometer to measure the viscosity after we make sure that the molecule dissolve. So this is really visualization is the main thing, but you can use it for kinetic. You can use it also for equilibrium. But again, you can do it in a blind cell if just equilibrium. You wanted to see gas, analyze gas and liquid. There is no need to do this. But visualization helps basically, especially related to the bulk. So that's what we have used this setup. And this setup is generally used for the hydrates.
I see. Thank you, Professor.
Sure.
Any other questions? Guys?
We can communicate, we can communicate with you. If there are other questions, something pops up later.
Sure. Rodrigo, would you like to ask?
Yes, please. Professor Abbas, regarding the parts of the presentation in the seminar that you were talking about hydrate formation using molecular simulations, we can see in the videos that you transmitted that it may form like hydrogen bonds, and in the video we can see the dynamics of the hydrate formation. I would like to ask which force field did you use, and if the bonding that we are seeing is just representation, or if you have a real bond forming in the simulation.
Basically, first of all, like anything you do with the molecular simulations, these are going to be step by step. You have to verify that the force field can predict some of the measurements. For example, in the case of C10, it's easy to see if you can predict the density, for example. For the case of some of these molecules, actually, you may see if you can predict the interfacial tension, for example. And for these molecules, because you see that they have amide, amine, ammonium, these are different types of nitrogen with different bonding, with different charges. So, this goes through all careful selection. And also, in the general rule, for those of us who have worked in the area, we see that, for example, the different types of interactions or different types of configuration of 2-3 atoms when they get together. The torsion, for example, is very key here. If the torsion is not included properly, you will not get a good result for any of them. You see these molecules here, I've shown them, they are extended. But when we look at the pictures which are representing what is doing, the torsion is a big element. So, there's all kinds, there is not one thing that we can say, and there is not one force field. So we have to basically go and select what we think is the right force field and then try to verify it to the extent we can. So these things we have done. For the case of water, there is no issue. There are different force fields. I don't know exactly. I don't remember what we have taken. For NC10, there is no issue. But for the two polymers, charge assignment and rest of them is going to be a consideration. But also there are limitations too. So I think we can go to further details. But my point is that here, for these type of molecules, which are basically, you can call it polymers, can call them all of them macromolecules or polymers, the torsion on the representation is critical. If you had aromatics, then what represent piper bonding is critical and should be examined. So what we did, for example, for the case of viscosification, what we did, because we were learning, or I was learning about DPD, dissipative particle dynamics. So I wanted to make sure that we are not really masking what some true physics. So the IFT data was there. So the first thing was that can we predict the IFT data, basically. So there are different things that we have done, and that takes effort and time.
Thank you very much. Going the same path of question, I would like to ask something that you just mentioned. It's very interesting how you can compare the DPD with the Florey Huggins or macroscopic data, and how you give the parallel with molecular dynamic simulations.
Right. Actually, what we did in this work, we first used molecular MD simulations, basically. Compare the result of DPD. Because it's very easy to make mistakes, very, very easy. So actually, we compared them initially. And now when I'm back, because we have more resources, I'm actually going to other theories to get the viscosity. For example, viscosity. When you are interested in rheological properties, it will take bigger system than if you're interested in equilibrium properties. So now that I'm back and I wanted actually to predict some of the new measurements we are doing, I'm actually looking at alternatives too, and using molecular dynamics simulation, but use certain theories so I can get results faster. But we have to do different things, but I was surprised that DPD could be used and results were very good also. But there are also parameters here. Whatever we do, we have some parameters we adjust. And some of these measurements in the report, actually what I've seen more and more, and this is not a accusation, but this is because we do work, human beings do the work. There's a lot of, in some areas, there's a lot of errors in reported results in the literature. And in the case of, especially in the case of CO2 viscosification, there are some simpler systems that sometimes there's one order of magnitude difference in different groups who do the measurements. So, that also molecular simulation can help, but we can do the matching. Actually, what I have now, I see that there are some issues for the application of Flory-Huygens theory, something which is widespread. I'm surprised. Our experience is that you cannot use the theory actually, or solubility parameter to get certain things that all of us do if we work with new molecules. So, everything has limitations too, but, that's what makes it interesting. A lot of effort.
Yeah. Thank you very, very much.
Okay. Thank you, Professor Abbas, very much for your time and for your beautiful presentation. Very exciting. I have so many questions, but I write to you later on. And thank you so much for today. And also, I'll thank all the students who took time to be here today also. So I think that's it. Thank you, Abbas.
Thank you, for the opportunity, and I enjoyed the conversation and presentation. Okay, bye-bye.
Thank you, Professor Abbas, for your time and your nice presentation.
Thank you.